Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to cover the Pythagorean theorem. So in this topic, we will apply the Pythagorean theorem to vectors, and we will look at an example. Now, you already know the Pythagorean theorem from secondary school. Given a right-angled triangle with sides length A, B, and C being opposite the right angle, then a squared plus b squared is equal to c squared. Now, given two vectors u and v, is there a relationship between the length of u, the length of v, and the length of the sum of these two vectors? Well, let's think about it. Here we have two vectors u and v, and the angle between them is greater than 90 degrees. When we add these two vectors together, it really does seem that the length of u plus v is actually less than either u or v. On the other hand, here we have vectors u and v where the angle between them is less than 90 degrees. In this case, if we add these two vectors, it's quite clear that the length of u plus v is greater than the length of either u or v. What happens if the two vectors u and v are orthogonal to each other? Well, here are the vectors u and v. I just picked two vectors that are orthogonal. This is the vector u plus v. Now, these are actually vectors, and in this case, they appear to be vectors in R2, but they could be vectors in any vector space. Now, notice that the vectors could be anything, but the length of the vectors. If we move v over to the other side, then the distance between the tip of u and the tip of u plus v, that is the vector v. At least the length of that distance is the magnitude of the vector v. So the hypothesis is the length of u squared plus the length of v squared equal to the length of u plus v all squared. Now remember, this is the 2 norm we're talking about. So the subscript 2 indicates that this is the 2 norm. The superscript 2 indicates that we are squaring the 2 norm. So is the square of the length of u plus the square of the length of v equal to the square of the length of u plus v? Well, that sounds like a theorem. Theorem. If u is perpendicular to v, that is, the inner product of u and v is equal to 0, then the length or the norm of u squared plus the norm of v squared is equal to the norm of u plus v squared. Proof. Now recall that the 2 norm squared is equal to, by definition, as being the norm induced by the inner product, as the inner product of w with itself. All right, in this case, we're actually going to let w be the vector u plus v. Thus, the norm of u plus v squared is equal to the inner product of u plus v and u plus v. Okay, now remember that the inner product is bilinear. So therefore, if we split apart the first component, we have the inner product of u and u plus v plus the inner product of v and u plus v. Now, if you didn't catch that, replace the second u plus v with a vector w. All right? Now, from the properties of the inner product, this is equal to the inner product of u and w plus the inner product of v and w. Now all we have to do is substitute back in u plus v into w to get the expression we just found. All right. Next step. Again, the inner product is bilinear, so that first inner product, the inner product of u and u plus v, is equal to the inner product of u with itself plus the inner product of u and v. The second inner product of v and u plus v is therefore equal to the inner product of v and u plus the inner product with v and itself. All right. Now, here's where we use our assumption. We assumed that u was perpendicular to v. Therefore, the inner product of u and v is equal to 0. Well, if u is perpendicular to v, then v is perpendicular to u, and that term is also 0. What's left? Well, the inner product of u and itself is the 2 norm of u squared. Also, the inner product of v and itself is the 2 norm of v squared. Oh, wait a second. Therefore, the 2 norm of u squared plus the 2 norm of v squared is equal to the 2 norm of u plus v squared. We're done. Thus, if the two vectors u and v are orthogonal, we can add them, and then the length, the 2 norm of u is the length of that vector, the 2 norm of v is the length of that vector, and the 2 norm of the sum is the square root of the sum of the squares of these two lengths. Let's look at an example. So here we have two vectors. U is equal to 0.5, 1.7, and v is equal to 5.1, negative 1.5. As you can see, the inner product is 0 because 0.5 times 5.1 is 2.55. And 1.7 plus half of itself, which is 0.85, is also 2.55. Only it is now negated because of the minus sign in front of the 1.5. So therefore, the sum of the first two entries multiplied together plus the sum and the product of the second two entries is indeed 0. The sum of these two vectors is the vector 5.6, negative 0.2. Now, the first vector is not trivial, and that second vector looks very close to 5.1, negative 1.5. So, is it true that the 2 norm squared of u and the 2 norm squared of v add together to give you the 2 norm squared of u plus v? Well, let's calculate it out. 0.5 squared plus 1.7 squared is 3.14. 5.1 squared plus 1.5 squared is 28.26. And 5.6 squared plus 0.2 squared is 31.4. And you will notice that 31.4 is equal to the sum of 28.62 plus 3.14. You can also see this visually by plotting these vectors on the plane. And yes, you can see that u and v do appear to be orthogonal, and u plus v is the sum of those two vectors. And it seems as if the Pythagorean theorem should indeed hold. So, following this topic, you now understand that the Pythagorean theorem actually does apply to orthogonal vectors and their sum. You understand the proof thereof, and it's actually reasonably straightforward. And you have seen an example of this theorem in R squared. However, it applies to all vectors of all vector spaces, at least all vector spaces that have an inner product defined. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!